Hey, this is Mel, and in this lecture, I'm going to be talking about some of the evidence for global warming. And so, in this class, you've been reading this book, and so far you've read parts 1, 2, 3, and 4. We've got exam number 3 coming up, and in exam number 3, we're going to be focusing on, among other things, the evidence for global warming. Now, you've been reading about other things, and some of those other things will be in exam number 4. So what I want to do in this lecture and the one that follows is go through some of these diagrams, the charts, the maps that have been in your book, and some of the concepts, and try to explain in more detail what they're talking about here, and hopefully they'll make a little more sense. So to start, here's an example of a graph that was in your book, and yours is very similar to this. It may not look quite exactly like it, but on the y-axis it says temperature difference compared to the 1951 to 1980 mean, and there's a bunch of red dots here, and each dot by itself represents a global temperature for a whole year compared to a 30-year average. Okay, so there's a lot kind of embedded in this, and I want to make sure we all understand what they're showing here. Okay, so first of all, each red dot. Imagine how complicated it would be to try to come up with one number to represent the temperature of the Earth. You've got all the different locations, you've got the different seasons, and you throw all that together over a whole year, and you come up with one number, and that's not easy to do. Now, with modern records, it's pretty easy with satellite data. We have satellites that can measure the temperatures of the surface of the Earth and come up with a number pretty easily. When you go further back in time, it gets harder. You've got to rely on weather stations on the ground and weather stations on ships and buoys, and you have to kind of integrate all these measurements, and people have argued about exactly the best way of doing it. And we don't have time to really dig into the details about how that is done, except we kind of have to accept that they know what they were doing when they came up with these numbers. So that's the first thing, is every red dot is one number for the whole planet for the whole year. The other thing that they've done, instead of saying that the global average temperature is a particular number, like 54 degrees Fahrenheit or whatever it is, they're not doing that. They're comparing it to a 30-year average. Now remember, we said in an earlier lecture that 30 years is a number that we use for calculating climate. We have this term climate norm, climate normal. It's a 30-year average. So what they've done here is they've taken all the temperatures for the world from 1951 to 1980, so that's a 30-year average, and they averaged the whole thing together and came up with one number, whatever that is. Let's just say it's 54 degrees Fahrenheit. And then they said, okay, how much did this one vary compared to that average? Now they're doing it in degrees centigrade, so the numbers above 0, so this dot right here would be 0.2 degrees centigrade above the 1951 to 1980 average. Okay, so between 1951, which would be right about here, and 1980, which would be right about there, these numbers are bouncing back and forth. They're hovering around the 0 mark because that's how they actually defined this graph. They're comparing it to this 30-year average. So the numbers that are in that 30-year time period are going to be pretty close to 0. On the other hand, you have these numbers that are negative, and what that means is that these years were colder than this 30 years. So it's, in my opinion, it's a very confusing way to show data like this, but this is how it's done. So we kind of have to get in the mind of a climate scientist. They always want to compare something to a 30-year average. So they pick this segment for their 30 years, and they're calculating each year, and they're comparing it to that 30-year average. So negative just means we were colder than this 1950 to 1980 average, and the positive numbers means that we're warmer compared to that 1950 to 1980 average. Okay, but the actual number isn't so important as the trend. So a big idea that I want you to get out of this class is that when we talk about climate change, we're looking for long-term trends in the data. Okay, that's a huge idea here. So if you go to year, right? So if I just pick some arbitrary year here and I say, well, here the temperature was relatively low, it jumps up and then it goes back down and back up and back down. And year to year, it doesn't show that it's actually getting warmer every single year. And this is a huge misconception. Some people say, well, global warming must mean it's getting warmer every year. But what this graph shows is no, it's not getting warmer every year. This year right here was colder than the year before, right? And so some climate change critics or global warming critics would say, aha, see, global warming is not real because we actually have years that were colder than the prior year. Therefore, it can't be getting warmer. But that's not what we mean by global warming. What we mean is that if you look at this graph, what's the overall trend? The overall trend is things are going up and up and up. And yes, there are year-to-year averages changes. Why, for example, do we have these? Why was it warm this year and then dip down the year after? A lot of this has to do with El Nino, La Nina. So in El Nino, you're exposing a big part of the equatorial Pacific warm water to the atmosphere. That helps warm the planet a little bit. In La Nina, you expose a lot of cold water along the equatorial region. That makes the planet a little bit cooler. So a lot of this kind of crazy up and down is La Nina, El Nino. We kind of, in our minds, have to kind of filter that out and say, okay, yeah, there's a lot of crazy up and down, but what's the overall trend? And the overall trend is higher and higher and higher temperatures, okay? It's worth pointing out, there is something weird happening here, and we did talk about this in the book a little bit. You can kind of get from this that from about 1910 or so onwards, we're warming, and then in the 40s we kind of cool off a little bit until the 70s, and we start to get warmer again, right? Well, why did this cooling happen? This is air pollution. The air pollution around the planet got so bad that it was actually reflecting sunlight and cooling things down. And if you remember in a previous lecture, in the 1970s, we passed the Clean Air Act in this country, and that helped clean the air quite a bit. In other countries around the world, we didn't really talk about them, but started to also pass similar laws. So we see that the atmosphere is actually starting to get cleaner after 1970, and that pollution is going away, and we see the warming then coming back as a result. Okay, so big picture here. Global warming doesn't mean it's getting warmer every year. It means that the overall trend is increasing temperatures. The fact that you have a year that's colder than the year before does not invalidate global warming. It's just, it is some noise in the data. That's what we say. Also, climate scientists typically do this funny thing where they compare it to a 30-year average. So if you're colder than that 30-year average, you end up with negative numbers. And that kind of, if you're not used to these kind of graphs, it doesn't make a lot of sense. Okay. Another type of graph that you saw was looking at the warming in your book. So this is on page 35, and it says change in global surface temperature 1901 to 2012. And then it says under that, notice that the pattern of warming is not uniform. Land regions, for example, have warmed more than the oceans. Okay, so there's a couple things I really want you to get from this. First of all, this gray, how it's gray down here and it's gray up here, that means that we haven't had temperature records that are robust enough for long enough to be able to say for scientific certainty what's happening. Now in a minute I will show you some graphs where we do kind of know what's happening here, but for this one, since back in 1901, there weren't a lot of people taking temperatures in the North Pole or the Antarctic, right? So we can't say 100% for certain what's changed there. And so that's why this is gray. That doesn't mean there's no warming. It just means we don't have records of it. Also, you'll see some other places in here where there's some gray, like in the middle of Africa. Again, in 1901, nobody's taking temperatures in the middle of Africa and making really nice records. So one of the big points that I want you to get from this is that the warming is not distributed evenly. You see a lot more of it on the continents than you do in the oceans, and you see a lot more of it in the northern hemisphere than you do in the south. So that's one thing I'd like you to notice. The other thing is, if you look at the scale down here, they're looking for changes over this 112-year period. Blue means it got a little bit colder in that 100 years, and all these other colors means that it's gotten warmer. And you'll notice that right up here, there is a little blob of blue, which means that, in fact, there's a couple little specks over here too. And so what this means is that the world has actually, there's a couple places where the world has gotten a little bit cooler in the last 100 years, according to this. Now, a climate change critic will say, aha, see that? Global warming must not be true, because if the world was getting warmer, then you wouldn't expect places to actually be getting colder. Okay, so this is another misconception about global warming. Global warming does not mean the entire globe is getting warmer, even though that's kind of the implication. So what global warming actually means is that if you mathematically average this whole thing, right, take all the colors into account, and you were to add it all up, what would the net result be, right? If you look at all the oranges and yellows and reds, yeah, there's a couple little specks here where it's a little bit blue, right? And those are where it's gotten cooler. But if you average this whole thing, the globe is definitely getting warmer. It's a mathematical average. Now, why would it actually be getting colder in places? Like, why would that even happen? So there's a couple reasons. One is you could have a shift in ocean currents. So if you remember the Gulf Stream comes out here and it takes warm water to the north. Well, that Gulf Stream is becoming weaker with time, which means it's pumping less warm water to the North Atlantic, and therefore this region up here is getting cooler. Here's another version of this map that is not in your book, but it's similar to it. And this one is a little different. What they're doing is they are again comparing the temperatures today to a 1951 to 1980 mean, right? So they're taking a 30-year average, and they're looking at temperatures today. And by today, I mean, I think this is a couple years old now, and comparing how the Earth is now compared to that 30-year period in the past, right? So if you do that, this is more modern. This doesn't go all the way back to 1901, so we have more modern records, and we see that a lot of the warming, the majority of the warming, is up in the north, okay, up in above the Arctic Circle. We also see there's more warming over the continents than the oceans. And we also see more zones here of cooling, right? There's more cooling here in the oceans. And again, why, does this invalidate global warming? No, if I mathematically average this whole picture together, I still get a number that's positive, right? It's the whole thing on average is getting warmer, even though there's places that are getting cooler. So again, why would places be getting cooler? There's several things that could be at play here. You could have changing ocean currents. You could also have changing patterns of storms. So think about the mid-latitude cyclones. If you change the direction of a mid-latitude cyclone, so let's say you increase the likelihood that the path of the mid-latitude cyclone will come down here, this region down here will have more cloudy days and will end up with lower temperatures. So when you see these zones out in the oceans that are cooler, doesn't mean the Earth's getting cooler. It just means we're probably changing directions of storms or directions of ocean currents, which are changing zones out in the ocean, but not necessarily changing the overall pattern around the Earth in terms of the overall temperature change. Okay, so this is a map that's not in your book, but it's pretty important. And what we're looking at is warming, and this map is actually for the past few decades, and we're looking at how much the atmosphere has changed temperature. So this is troposphere up here, and what we're looking at really is how the temperature is about 10 kilometers above our head has changed. Okay, that's what they're showing. So the colors are similar as the other maps. Red means that it's getting warmer, blue means it's gotten colder, white means it hasn't changed, gray means we don't have any data. Okay, so notice that there's some big differences between this one and the last maps we were looking at. So one difference is you don't see the big contrast so much between the continents and the oceans, right? You still kind of notice more warming up here to the north, but the big thing I want you to pay attention to on this map is how we have a band that's right through here, and we have another band that's right through here. Okay, so in other words, all of this pink has been getting warmer, but the areas that have been getting especially warmer are centered kind of right through here and right through here. So I want you to think about something that we talked about in a previous lecture that kind of lines up with this and this. And if you can remember what we talked about in global circulation in that lecture, is we talked about how air rises along the ITCZ, which is kind of near the equator, but then it sinks back down about 30 degrees north, 30 degrees south. And those are called the subtropical highs. And they change with the seasons. Okay? Well, right through here, that's about 30 degrees south, and right up here is about 30 degrees north. So what we see, for example, is like right through here, this is one of the an area that we expect to find one of the subtropical highs, and we see that it's gotten even warmer than the surrounding area. This is where we expect to find the Bermuda high. It's gotten even warmer than usual. This is where we expect to find the Pacific subtropical high. It's gotten warmer than usual. And even here over the continent is also part of the Pacific subtropical high sometimes. So what does this mean? Sinking air warms. Okay, we talked about that a long time ago. If I have the Hadley cell, air rises at the equator, sinks along 30 degrees, right? That's the whole Hadley cycle. If I make the Hadley cell bigger and stronger, I have more air rising at the equator, which means I have more air sinking at 30 degrees, which means I have more of the compressed air warming than I did before. Okay, so in a world where there's no global warming, okay, we expect air to rise at the equator, we expect air to sink at 30 degrees, and as it sinks down, it warms, but it's reaching a state of equilibrium, right? Well, what this is saying is that those Hadley cells are getting stronger. They're getting bigger and they're getting stronger. And even though it's getting warmer everywhere, we're seeing especially large amounts of warming where the Hadley cells are coming down and making those subtropical highs. You're compressing more and more air coming down, which makes it warmer ultimately will make it warmer and drier at the surface. Okay, so why would this happen? If you warm up the whole planet, remember, why is air rising at the ITCZ in the first place? That's the warmest part of the Earth. That's where the trade winds converge. So if you warm up the whole planet, this part along the equator at the surface is getting warmer. More air is rising. More air goes up to the stratosphere. More air sinks down about 30 degrees north-south. And we get stronger subtropical highs. So what does that mean for us? Well, remember, we are living under the influence of the Pacific subtropical high, especially in the winter and the spring and the fall, right? It moves out of the way in the summer, but the rest of the year it really dominates our weather. Us in New Mexico in the southwest. So if that gets stronger, then what does that mean for our weather? That means that our Pacific subtropical high will be getting stronger. We'll see more days of clear skies, less days of rain. So overall, what this is telling us is as global warming continues and as the Hadley cells are getting stronger, we can expect more clear skies and less precipitation in the future. So another way that we can look at evidence for climate change is to look at something that we call a time series of temperature. And the very first graph we started off with in this lecture was a time series of temperature for the whole planet. But you have a project this week and it involves making a time series of temperature for a particular location. And so I'm going to kind of show you how that's done and show you the type of graphs that you're going to be making. So we can divide up the country into these areas called climate divisions, and it kind of looks like counties, but they're bigger than counties. And all the areas within a climate division are supposed to have similar climates. There's something similar about them. They have similar topography or elevation or something, and so we kind of group them all together. So within each climate division, you might have, say, several hundred operating weather stations. And usually these weather stations are recording data at least once an hour, sometimes once every 15 minutes, or even more often than that. And so what we're going to do is we're going to pull records from a climate division, and we're going to look at, we can look at how the temperatures have changed in the past. So here's an example of a record that I pulled from a climate division called the Northern Mountains Division. So if I go back here, this blob right here, that's the Northern Mountains Division. And so what I've asked this to do, and this is what you'll be doing on your project, is I've generated a series of these. Each one of these is red dots, represents a month of data from hundreds of weather stations across this whole region of the Northern Mountains Division. Okay, so this dot right here means that the computer went to the database and it looked at all the records for this month. So this is December of 2014. Okay, and it looked at all the records kept by all the weather stations in this area, day, night, the whole thing, averaged the entire thing together and come up with one number for that entire month. And that's what's plotted here. Okay, so every one of these dots is one number for the entire month of that particular year, averaged over this broad area with all those weather stations, which are recording usually day and night, at least once an hour. Okay, so this is what this record looks like, and I went back a few years, and you can see there's this up, down, and that's just the seasons, right? So summer, winter, summer, etc., right? And so from this record, if I asked you, do you see any evidence of climate change, it'd be pretty tough to see anything, because it's just, what you're seeing is the seasonal swing, right? Okay, so now what I'm going to do is I'm going to go back more years. So now I'm going to go back 20 years and look at how the temperatures have been changing. So now again, you can see summer, winter, and again, if I asked you, do you see any evidence for changes, it's probably kind of hard to see a lot here. There's a lot of crazy up and down. What if I go back even further? So now I'm going back to 1940. So at first, it just looks like a crazy bunch of up and down lines, but you can start to use a graph like this to notice a few changes with time. So let's look at the winters. Okay, so there's these horizontal lines. Like here's a line that says 24 degrees. Notice how many winters in the past got colder than this 24-degree line, right? And then notice what happens after 1990. You see no more winters get colder than that 24-degree line. Now let me add, remember what this means. That dot right there doesn't mean the winter got down to 24 degrees once. That's average day and night over a whole month, right? The entire month averaged below 24 degrees. That's what we're talking about here. But notice, you can see that how often the winters got down to that 24-degree line and how often they went below that in the past. And then starting about 1990, there's a few that reach that line, but nobody gets any colder below that. Or you could look at the summers and say, okay, notice that, here's a 69-degree line for reference, and you can see how often the summers reach that 69-degree line and either met it or maybe went a little bit past it. And if you just we're just eyeballing this, notice how much white space there is between, say, the 64-degree line and the 69-degree line. And then notice how much closer these recent summers are to that 69-degree line. There's a lot less of that white space in here, and you can kind of see, really, the number of summers that surpass that 69-degree line maybe isn't that different, but you can see that overall they're getting closer and closer to that 69-degree line. And again, 69 degrees doesn't sound that warm, but this is averaged over days and nights, and we're in the northern mountains, so a lot of this is high elevation data. Or you can even go further back. So now what I've done is I've gone all the way back to 1908, right? So I've got 100 years of data here. And I'm going to use the same tricks. Notice how often the winters got colder than 24 degrees in the past. And then notice that stops over here. And then notice how often we get close to that 69-degree summer. And then notice how often we do it in modern times. So you can just kind of eyeball these and notice if there's any changes in the long-term trend. There's obviously a lot of noise, what we call noise in this, where we had warm years and cool years and warm years and cool years. But what's the overall trend? That's what we're interested in when we're talking about climate change. So here's another one, for example, coming from, now we're in the Cascade Mountains in Washington State. And we're looking at 100 years of data. And the same tricks. Notice how often the winters got below this 22-degree mark, right? You see these cold winters, and then notice, starting in the 80s, you no longer see that, right? And in fact, starting in the 90s, they don't even hardly get below this 27-degree line. On the other hand, we can look at the summers. How often did the summers reach this 62-degree mark? Notice how much white space there is between the 57 and the 62. And then see what happens here, that we start to get summers that are warmer than the 62-degree mark, and that white space between those two lines disappears. And so we're seeing a shift towards warmer and warmer summers and warmer winters. And in fact, when we do the math with global warming, the biggest changes that we're seeing in terms of temperatures is we're seeing warmer nights and we're seeing warmer winters. Yeah, we're seeing some warmer summers too, but the biggest change, like mathematically, that's happening is the winters are getting warmer and the nights are getting warmer, and that's due to the extra greenhouse gases. Okay, so besides just eyeballing some data that's going up and down and trying to figure out whether it's increasing or decreasing, scientists have more quantitative ways of dealing with this, and I'm going to teach you one method that we use. It's called a running mean, or a running average. So here's an example. Here we've got temperatures from days as they're going by. So let's just say that each one of these dots represents the average temperature for that 24-hour period. So we've got temperature on the y-axis, we've got days on the x-axis. And when I look at this data, I can see there's a lot of up and down, right? So temperatures are going up and down. And what I'd like to know is there a overall increasing trend or decreasing trend or no trend in this? Okay, that's what we're trying to figure out. So what I'm going to do is apply something called, in this case, I'm going to call this a 5-day running average. Okay. All right, so here's how this works. First, I'm going to take the first 5 days, 1, 2, 3, 4, 5, and I'm going to make like a window of this first 5 days of data, and I'm going to calculate what the average is of that 5. I'm going to plot it in the middle of the window. Okay, so my first 5 points are 34, 41, 37, no, 5, 6, 7, 38, sorry, 38, 42, and 45. So I just add those all up, I divide by 5, and I get an answer of 40. Okay, so the average of all of these is 40. So I'm going to plot it right in the center of my window. So there is my first point. All right, so I just took the average of 5, plotted it in the middle. Okay, so now I'm going to take this window, and here's the key. I'm going to move it over 1 day. Okay, so I'm going to draw another one right here. Here's my new window. Okay, so I just shifted it over one day. And I'm going to calculate the whole thing. All right, so I got 41 and 38 and 42 and 45 and 34 divided by 5, 40 again. Okay, so my new window, my new calculation is exactly the same answer as it was before. So I plot that in the middle. So then I'm going to shift it over one more. So over one more. And again, I'm going to calculate this new batch. So 38, 47, 45, 34, and then my new point is 43 divided by 5, 41.4. So now the center of this window, 41.4, something like this. So I'm starting to build this new graph of red dots that is the long-term trend. And so what I see is at first there's basically no change in the long-term trend. Now it's starting to move up. And I can keep doing this by moving this window over and over and over and doing these calculations over and over and over, and I'll get another line that tells me what the long-term trend is. It's called a running average or a running mean. Very tedious to do this by hand, but easy for a computer to do. So part of what you're going to do in your project is when you get some of these temperature records, you're going to tell it to calculate the running mean, and it will just put it on your graph. So I'm going to show you some examples here. So here's an example of one of these graphs where I have used a running mean, and I just asked the computer to do it. I didn't do any math myself. And this is a 12-month running mean, and it produces this blue line. So it takes every red point and takes 6 months ahead and 6 months behind and calculates what that running mean is and plots it as blue. Okay, so now what you can see is the running mean, and we're back in Northern Mountains Division. The running mean is bumping up and down between this 44-degree mark and the 49-degree mark, right? It's kind of down here. And then you see when you get to the 90s, it stays closer to this 49-degree mark and doesn't ever go back down to this 44-degree mark. So the long-term average has increased. It's averaged from somewhere kind of down in here to somewhere up in here. Okay, or another example, here's one from Arizona. And so here, again, 12-month running mean, you can see that it's somewhere here in the, it's bouncing back and forth between 61 and 63 degrees back in the early part of the 20th century. And then when we get to the last 20 years, it's now jumped up between the 61 and 63, the 63 and the 65 degree mark up in here. Okay, so we've seen a shift in the overall long-term trend. So this is how you're going to use the running mean. You can have the computer calculate it and then look at it and see if there's any trend. Now, what if there was no trend? If there was no trend, then what we would see is we might see some up and down at the beginning of the century, and it would just kind of remain that same pattern all the way across till today. And that's how you would know if there's any long-term trends in the data. So when climate scientists are talking about global warming, what we're looking at is we're looking at actual temperature measurements for the most part. And so in modern times, say the last 30 years, that comes from mostly satellite data. We've got satellites that can measure the entire temperature of the Earth every day. You go before satellites, then you're looking at weather station data, and before that, just thermometers. And the farther back you go, the more difficult it is to really get some good data. Now, as scientists, that's what we look at when we're trying to figure out whether the Earth is actually warming or not. And there are some, in popular media, a lot of times you'll hear that the reason that scientists know that the Earth is warming is because of glaciers are doing this, or the polar bears are doing that. And those are effects of global warming, but that's not really the evidence. The evidence really comes from the temperature data. But I want to talk about some of this other evidence because you'll hear about that. And one of the things that we can look at that lets us know that the Earth is warming is the decrease of ice on Earth. Okay, so one example is we can look at how much snow is on the ground in the northern hemisphere during the spring. And one of the themes of this whole lecture is that when we're talking about climate change, we're not looking at what's happening from one year to the next, but it's the long term, right? And so you can see from this that from year to year, we have years where there is relatively high amount of snow, and then we have relatively low amount, and it bounces back and forth. But the overall trend is kind of this downhill slope here. And if we go to something like the Arctic sea ice, which is the sea ice up around the North Pole, here's a graph looking at the Arctic summer sea ice extent. And again, we see ups and downs, but there's this overall trend headed downhill. So that's kind of what we're seeing for climate change. And again, just to reiterate, we're not looking at this and concluding that the Earth is getting warmer. We're looking at the temperature data and concluding the Earth is getting warmer. But this is another thing that we can see as evidence. So here is a animation showing the extent of the Arctic sea ice from year to year. And I've got it paused right now, but just orient yourself. So here's Canada, there's Alaska right there, and then here's Siberia. And notice how close the ice is to the margins of these continents, okay? And these images you're going to see is the extent of the ice in the summer, okay? So in the winter, it pretty much always reaches out to the extent of the boundaries here. Okay, so let me play this. So year to year, notice how the margins of the ice change. And some years are colder and there's more ice. Some years are warmer, there's less ice. But we're looking for the overall trend. And notice that in some summers, the ice actually doesn't even reach the land masses in some instances, which means it opens up the seaway that didn't used to be there. Okay, now this is a little obsolete. It ends in 2011. Since this was made, the sea ice has actually decreased even more. Now we're going to look at the same data, except we're also superimposing a time series graph. And this is again to illustrate the point that I keep trying to make, which is that climate change is not something we observe year to year. It's a long-term trend. And so even though we can see that some years there's more ice and some years there's less, the overall trend is one of going downhill. And that's what they're showing here on this plot that they've superimposed on the same movie that we just saw. Okay. So along with that is the fact that we're seeing a lot more melting of continental glaciers than we saw previously. And so Greenland is one of the examples where Greenland is one of these places that we've been drilling ice cores because it has not melted for hundreds of thousands of years, and yet now we're seeing sort of record amounts of Greenland starting to melt. And it makes for some very spectacular photos like this waterfall here, but that's not supposed to be happening. And it's kind of a shocking amount of ice that's been melting. So here's just a 3-year study from 2004 to 2007. Greenland lost amount of ice equivalent to 14 states. Of course, they pick little states, but still, each of these 3 feet thick. That's a significant amount of ice that it lost. Now, there's still a lot there, so it's not going to be disappearing. Even in a few years, it's going to take a while. But we're seeing record amount of ice melt coming off of Greenland in the springs and summers. So here's a news report from a couple years ago. Scientists incredulous at abnormally high numbers for April. Record melting across 12% of the ice sheet. So that's more than they ever seen before this time of year. Also, we can look at glaciers, and we can look at where the glaciers were about 100 years ago. So I've got some before and after images. And again, if you watch popular media programs on climate change, they'll kind of frame this as scientists look at this and we can tell that global warming is happening because of this. I want to emphasize that this is one of the effects of global warming, but this is not great data for scientists. This is one of the effects. So here we are, a glacier, so before and after picture 100 years apart, and you can see the glacier in the foreground and nothing left but a little patch of snow in the background on the modern picture. Here's another one from 1920. Again, you can see the glacier here and this little ice field about 100 years later. This glacier, here it is in the background, no sign of it anymore. Or this one, which is now way back there. And you can see these, pictures from like this all over the place where there are glaciers. That there's, if you look 100 years ago, you see this big difference, right? So here's Olympic National Park, the before and the after, right? Or this one, the before, and there it is way in the background, the after. This is a little bit of it's kind of a confusing image. We're looking down from space. This is the top. The glacier flowed downhill this way, and this is it melting, and chunks of ice are floating in the water here. So these lines are what we call the old terminus. This is where the glacier used to be. So in the 1851, this is where the glacier ended. This was the terminus. And then as 1902, this is the terminus, headed uphill. 2000s, it's up here. The last mark on here is actually over 10 years old now. It's 2006, and they need to update this image, but the glacier is now somewhere back here. So it's been retreating every year, more or less, as the climate has gotten warmer. Other evidence that for our warmer temperatures is that the sea level is rising. Okay, now our records of sea level get more and more sketchy the further back we go. So you'll see there's several lines here. So this is year 1900. This is millimeters above. They picked a 30-year average again. They didn't tell us where it was, but there's a 30-year average that they're comparing this to, and they're comparing how much global sea average has changed since some particular 30-year period. And there's different lines because they've been measuring different ways. There's different techniques for trying to figure out the global sea level. And then suddenly you see the lines get thinner, and that's because we start measuring them from satellites, and it becomes a lot more accurate. Now, your book talked about this a little bit, but just to make sure you didn't miss it. There's two reasons why the oceans are rising. Number one is the one that everybody probably can guess. If you melt ice, that ice goes into the sea, and the sea level rises, right? You melt glaciers, sea level goes up. But that's actually the smaller component. The more significant reason is because when you warm up water, it actually expands a little bit. So as the oceans get warmer, the entire oceans, all of it is starting to expand just from warmer temperatures. So those two things together are why the oceans are rising. Now, once we got satellites that could measure the ocean from, basically it's like using radar where they beam down and they hit the ocean, they bounce back, and they can measure it pretty precisely. We got satellites that can do that starting in the early 90s. And what you can see, the dark blue is kind of the up and down changes year to year of the sea levels. But the red line is sort of the trend line, the overall trend. And the overall trend is that the seas have been increasing at about 3.4 millimeters per year. Okay, so that's not huge, right? 3.4 millimeters, that's not a lot, but it's starting to add up over the decades. It especially is becoming noticeable if you live pretty close to sea level. So this is not a hurricane or anything weird. This is just a high tide. The town in Florida that's built pretty close to sea level. And we can see that now the ocean is starting to come in where it didn't used to come before. In fact, there are these cities along Florida where places that didn't hardly ever used to flood, except in rare events, are starting to flood on a regular occurrence now. And water's coming up in the storm drains, and it's not coming from the ocean, it's coming up the storm drains and flooding the streets now, because those areas are now starting to become below sea level when they didn't used to be. Another way that you can see this is just another example from Virginia and Norfolk. So this is along the coast, and this is kind of a weird graph. It's hours per year of flooding in this particular neighborhood. So somehow or another, I don't know who thought of this, but they started to record how many hours per year this particular neighborhood was under flooding. And so back in the 30s is when they started this. And you can see that as time has gone on, they see more and more hours of flooding in this neighborhood. Again, this is not great data for scientists because there could be other things that contribute to flooding in the neighborhood, how how the streets are being maintained and how the storm sewers are being maintained and all that kind of stuff. But it's just another illustration of how rising sea levels are affecting some neighborhoods. So, to conclude, we've got evidence that the temperatures are increasing in the summers, in the winters, in the days, and the nights, especially during the nights, especially during the winters. We see it over the continents, especially. We see it over the oceans, some. We see it up in the atmosphere. Okay, we've talked about all those things. Also, what we've seen in the previous lecture is that greenhouse gases are higher now than they've been in the past million years or so, probably more, but we can say for sure in the past million. So we know the temperatures are higher than they've been in a long time. We know the greenhouse gases are higher than they've been in a long time. We know how greenhouse gases work. So the question is, can we say 100% sure that the extra greenhouse gases are changing the climate? Or could there be some other factor at work? So, what is another way that Mother Nature could possibly change the climate? How could we make the Earth warmer? If it's not humans producing greenhouse gases, what else could it possibly be? Well, one thing it could possibly be are sunspots. So the sun, it turns out, is not at a constant luminosity. It goes through these 11-year cycles of sunspots. And the sun has these magnetic storms, and they're not very well understood. But what we do know is that the sun has these cycles of 11 years where it goes through periods of more sunspots and then periods of less sunspots. Now, here is what is counterintuitive. When you have a sunspot, the sunspot is dark because it's cooler than the surrounding area. And you'd think, okay, if the sun has more sunspots, it should be cooler. But it turns out that when there are sunspots, the area surrounding the sunspot is actually extra hot. It makes up for the sunspot, and more than makes up for it. So when you have a sun with more sunspots, the sun is actually hotter by a few degrees. And it's not huge, but it's enough to make a difference with the climate on Earth. So more sunspots means a hotter sun. And again, that's counterintuitive. You'd probably think that more sunspots would be a cooler sun. So people have been counting sunspots ever since the telescope was invented. And so here's an example of a peak where there's a peak in the 11-year cycle and then a decrease in that 11-year cycle, then a peak 11 years later, and so forth. So every 11 years, we have a peak in the sunspot cycle, and then they decrease again. So here is a movie of sunspots, and before I start it, notice they've got yellow and they've got blue here, and sunspots have a north and a south, so they're magnetic, and so that's what the two colors mean. And we're going to look at a quick movie, a time lapse of several years of sunspots. So it's going to rotate it first to show you here's an active sun with a lot of sunspots, and then it's going to kind of split it apart so you can see the whole sun as a big map. And then it's going to play, we're going to look at 3 decades of sunspots. So notice they kind of disappear. There's the minimum of sunspots. Now they come back, maximum, that's 11 years later, and then they disappear. Here comes the next cycle. So every 11 years we see this maximum and then back down to minimum again. That's the sunspot cycle. And each time it does that, the sun is a little bit warmer during the maximum and a little bit cooler during the minimum. So one of the things that Galileo did as soon as he invented the telescope is he started observing sunspots. So we've got an actual record of sunspots all the way back to about 1610 is when he started doing this. And one of the weird things that happened in the late 1600s is the sunspots went almost disappeared completely for several decades, like half a century. It's called the Maunder minimum, and for whatever reason, the sun went into kind of a relatively low activity state, and we had very few sunspots decade after decade. Well, that period of low sunspot activity corresponds to something that we call the Little Ice Age, and it was a period where the Earth was actually a little bit cooler than usual. Not full-on ice age with like glaciers coming down and all that, but if you look at the historical records, farmers had a hard time during the Little Ice Age. A lot of crops failed because the Earth was relatively cooler than it was supposed to be. And then we also see there's some other times, say in the early 1800s, where the sunspot number was a lot lower than it was supposed to be, and there was a measurable cooler Earth, just by maybe half a degree or something like that, but that makes a difference. Well, so some critics of modern day global warming science will say that, oh, the reason the Earth is getting warmer today is because of sunspots. Okay, so let's look at that. So we count sunspots today, and this curve followed by this curve are the last two solar cycles. So this is the last solar cycle, and this is the one before that. So the one before that peaked in about 2000, 2001, and the black dots are how many sunspots are being counted, and the blue is like a running mean. So they're using the same math that we did earlier. So you can see, okay, it looks like the sunspot cycle back in 2000, 2001 peaked at, whatever, 125, whatever this level is here. So then the sunspots decrease, right? So that's this part. And then they ramp up again, and it's supposed to peak 11 years after this. But instead of peaking up here, like the previous one, it's peaking down here. And so we have actually had a relatively inactive sunspot cycle in the past, this past sunspot cycle. It's supposed to be up here. We had fewer sunspots than we're supposed to. So the sun is actually cooler than it's supposed to be. So the argument that sunspots are somehow making the climate warmer are exactly backwards. The amount of sunspots we have is lower than it should be. So if the sunspots were back up where they ought to be, we ought to see a climate that's even warmer than we have today. So another thing you will hear from climate change deniers, and these are the people who think that there either is no climate change, or if it is, it's naturally occurring. They will say that volcanic eruptions are what's behind climate change. And usually what they say is the amount of greenhouse gases coming out of a volcano is greater than that produced by humans. Now, one reason you already know why that's not true is because when we looked at the Keeling curve, remember that? That's the curve of CO2 going up and up and up a little bit each year. If the amount of greenhouse gases coming out of volcanoes was significant, then you would see a big jump every time there was a volcanic eruption. But you never see that. And in fact, all the CO2 sensors around the world that monitor how much CO2 is in the atmosphere, they don't do anything when you have a big volcanic eruption. It's just not enough CO2. So that's not the reason. But there is a reason that volcanoes can change the climate. If you have a big volcanic eruption, and this is the last really big one, sort of in our lifetime, was Pinatubo in the Philippines in 1991. This big cloud you see is something called volcanic ash, and it's little tiny microscopic pieces of rock, and it's mostly glass. And if it's a really big eruption, this material will get ejected up into the stratosphere. And when it gets up into the stratosphere, as we learned in a way early lecture, there's no weather to remove ash from the stratosphere or anything. There's no weather up there. There's no clouds. There's no precipitation. And so it goes up and it spreads out. And one of the things that it does is it blocks sunlight and it cools the planet. So for example, here's a little time-lapse movie of a poignant style eruption. And so this is the ash coming up. And you might see some lightning in there too. This looks like the anvil from a cumulonimbus. And this marks the top of the stratosphere, or the top of the tropopause in the beginning of the stratosphere. And you can see, once in a while, you'll see some ash punching through, and going up into the stratosphere. And so that ash, once it goes up into the stratosphere, will stay up usually like a couple of years before it finally gets removed. See, right there you can see it going up into the stratosphere. So this will have a change in the climate, but it has a cooling effect, not a warming effect. So we have instruments that actually measure how much dust is in the stratosphere. And this is the readout from one of these, and let's see if we can make sense of this. So what we're looking at is a graph. Let's ignore the color one for now. And we're looking at this black and white graph. This is how much dust is in the stratosphere as the years go by. So this is 1985 moving forward. And we see there's a big spike right here in the amount of dust in the stratosphere. That's Mount Pinatubo. And then it decreases and takes several years for it to come back to normal. Well, during this time in here, after Pinatubo erupted, we saw that the world global temperature decreased about 1 degree or 1.5 degrees centigrade. So it actually changed the climate. And you can see these little bumps here. These are smaller volcanic eruptions that also put ash into the stratosphere, but at a lesser amount. If you go back in time, you can see that we've actually had some volcanoes much larger than Pinatubo. Every one of these little spikes here has been a big eruption, kind of like the one we just saw in that movie, except bigger. And there has, this goes way back, hundreds of years, but for the periods of time that we actually have written records, what we see is that every time there was a really big eruption like Krakatoa, there was actually a recorded cooling event afterwards, a lot of crop failure. In modern times where we actually had temperature measurements, we can measure that we had a cooler summer that followed. So every one of these big ones probably resulted in a dip in the Earth's temperatures for a year or two following that eruption. So if we take all the sunspot records into account and we take all the volcanic eruption records into account, we can reconstruct the climate of the Earth in the past several hundred years, and what we see is that we can explain pretty much all of the changes in Earth's climate over the past several hundred years, except for what's happened in the past 100. The warming that we're seeing in the past 100 years cannot be explained with volcanoes or sunspots. And we're left with really the only thing remaining, which is human greenhouse gases.